Right. Today we are going to be talking about power relationships in three-phase systems. So let's first start with instantaneous and average power. So let's say that we have a delta connected three-phase load. And in this particular instance, we're going to look at what happens with a Y-connected load. Our results should be fairly similar to what we would see for a delta connected load as well. I'll explain what I mean by that in just a moment. Okay. So across our three-phase load, we will have some voltage VAN, VBN, and VCN. And we will also have some phase currents IAN, IBN, and ICN. And I'm going to say that, let's see, VAN is equal to VP angle 0 degrees, VBN is equal to VP angle negative 120 degrees. VCN is equal to VP angle negative 240 degrees. And all of these are measured in volts RMS. Similarly, I can say that my line currents, IAN, excuse me, not my line currents, my phase currents are going to be IP theta I plus 0 degrees, IBN is going to be IP angle theta I minus 120 degrees, and ICN will be IP angle theta I minus 240 degrees, and all of these are measured in amps RMS. I'm actually going to change, I'm going to change the angles of our voltages really quick here. My apologies. I'm simply going to express it in terms of some generic phase voltage theta V plus 0 degrees. And then we'll have theta V minus 120 degrees and theta V minus 240 degrees. So that we're as generic as possible. We don't have any specified phase angle theta V or specified phase angle theta I. So each of these signals has a time domain equivalent, right? So we could say that VAN as a function of time is going to be root 2 VP cosine omega t plus theta V plus 0 degrees volts. And let's call root 2 VP VM, which is just the magnitude of our sinusoidal voltage. And obviously VBN of t would be 120 degrees behind that. VCN of t would be 120 degrees behind VBN. Similarly, our currents will have a time domain representation. IAN of t, that would be root 2 times IP cosine omega t plus theta I plus 0 degrees amps. And we're going to call root 2 IP IM, which is just the magnitude of the sinusoidal function. So our instantaneous three-phase power as a function of time is just going to be the product of the time domain signal VAN, sorry, there shouldn't be a squiggle there, T times IAN of T. I need to be consistent about my subscripts, plus VBN of T, IBN of T, plus VCN of T, ICN of T. If we apply that exact same trig identity that we did when we were dealing, excuse me, with single phase power relationships, what we're going to wind up getting is 1/2 VM IM cosine theta V minus theta I plus 1/2 VM IM cosine twice omega t plus theta V plus theta I, where this part right here is specifically for the A phase of our load. And then we're going to have 1/2 VM IM cosine theta V minus theta I plus 1/2 VM IM cosine twice omega t plus theta V plus theta I minus 240 degrees, which is for the B phase. And then 1/2 VM IM cosine theta V minus theta I plus 1/2 VM IM cosine twice omega t plus theta V plus theta I minus 480 degrees. Okay. Now, I want to point something out here. Minus 480 degrees is the same thing as minus 120 degrees, right? Because it's just 120 degrees and then we go one more full loop around the circle. So when we added three complex numbers together where the phase angles were separated by 120 degrees, so 0, negative 120, and negative 240, we found out that the result of adding those three terms together was 0, which means this term, and this term all serve to cancel each other out, leaving us with an instantaneous power that is simply 3/2 Vm Im cosine theta v minus theta I. Now, what's really interesting about this is that our instantaneous power, our power as a function of time, is actually independent of time. So the instantaneous power is a constant value. Since it's a constant value, this is also the average power. So in a three-phase balanced system, the instantaneous power and the average power literally represent the same quantity. And what that effect has is that for, say, a three-phase induction motor or something like that, since the power that's being absorbed by the motor is constant, the torque that's being developed by the motor is also constant, which means the motor does not mechanically vibrate, or the magnitude of the vibrations is very, very small, okay? It has nothing to do with the power that's being delivered to it. This is one of the biggest reasons that the industrialized world has adopted three-phase power for its power distribution systems. Is it works perfectly with induction motors to give the best possible response. Now we can express this term 3/2 Vm Im cosine theta v minus theta I in terms of our phase voltages and our phase currents, right? So 3/2 √2 Vp times √2 Ip cosine theta v minus theta I looks like 3 times our phase voltage times our phase current cosine theta v minus theta I, where it doesn't particularly matter if my phase voltage is corresponding to a Y-connected source like we have derived it, or a delta connected source. We would actually get the exact same result as long as we used phase voltage and phase current quantities, okay? So this is our discussion of instantaneous power and average power. We get a single constant value. That's pretty fantastic. Now let's look at what happens from a complex power perspective. I'm going to scroll up here and I'm just going to steal this diagram. We're going to use the exact same thing. So the complex power absorbed by our three-phase network is simply going to be the complex power that's absorbed by the A phase of the load plus the complex power that's absorbed by the B phase of the load, plus the complex power that's absorbed by the C phase of the load, treating it very similarly as we did our instantaneous power example, but we are simply using our complex power relationships. Well, the complex power absorbed by the A phase of the load, SA, is by definition VAN multiplied by IAN conjugate, which is going to be the magnitude of VAN multiplied by the magnitude of IAN with a phase angle of theta VAN minus theta IAN, which is the magnitude of VAN times the magnitude of IAN angle angle theta ZY, because theta VAN minus theta IAN has to equal the angle of the impedance. For complex power absorbed by phase B, we get VBN IBN conjugate, which is the magnitude of VBN times the magnitude of IBN angle theta VBN minus theta IBN. Well, the magnitude of VBN is the same as the magnitude of VAN, so we can just write VAN here. The magnitude of IBN has to be the same as the magnitude of IAN in a balanced three-phase system, so we can write IAN here. And our angle will still just be the angle of our impedance ZY. So the complex power absorbed by phase A and the complex power absorbed by phase B are equal. It should be obvious to see then that the complex power absorbed by phase C is also just going to come out to be the magnitude of VAN times the magnitude of IAN with an angle of theta ZY. So using these results, we can see simply that our complex power is 3, the magnitude of VAN times the magnitude of IAN angle theta Z. Now let's look at this from a slightly different perspective, okay? So our three-phase power is 3 times the magnitude of VAN, which in this case is simply our phase voltage, times the magnitude of IAN, which is simply our phase current. And then we have our angle theta Z. Okay, so this is our three-phase power expressed in terms of our phase quantities, right? So phase voltage and phase current. What is incredibly interesting is that we can use this relationship to determine what happens from delta connected systems as well. So let's say that instead we had a delta connected load, right? So in a delta connected load, our phase voltages and our line voltages are literally the same thing, okay? So I'm gonna put equals, And then since our phase voltages and our line voltages are the same thing in a delta connected load, I'm going to put VL here because that represents what our line voltage is going to be. We also know that it still has to be related to the angle of the impedance, theta Z. But now we need to figure out what's going on with this 3 and IP. Okay. So for delta connected load, here's my transmission line. Here's my lowercase a terminal. Here's my uppercase a terminal. And let me go ahead and draw the other set of transmission line quantities. So here's ZW, B, here's uppercase B, and here's our C phase. Here's our uppercase C. I'm just doing ellipses on the left-hand side because it literally does not matter if we have a Y connected source or a delta connected source for this discussion. Here we have our impedance, Z delta, between our A and B terminal. Here's the impedance, Z delta, between our B and C terminals. Here is our impedance, Z delta, between our C and A terminals. So our line currents are IAA, IBB, and ICC. And our phase currents are IAB, IBC, and ICA. We perform Kirchhoff's current law at node capital A. What we will find is that we have a current of IAA flowing in from the left, and then we have a current of IAB minus ICA flowing out into our load. Okay. From this, we can see that IAA is simply IAB times 1 angle 0 degrees minus 1 angle negative 240 degrees, or IAA is equal to IAB times √3 angle negative 30 degrees. What's key here, though, is that we can recognize that the magnitude, let me put this here, the magnitude of our line current is then simply square root of 3 larger than the magnitude of our phase current. Using this relationship, we can put IL here, and since this term was originally 3, but IL is square root of 3 times larger than IP, we put a square root of 3 here, and we now have a term for, or excuse me, an expression for our 3-phase complex power only in terms of line quantities, okay? So our left-hand representation is for phase quantities. our right-hand representation is for line quantities. And if we need to, we can always go back to effectively our single phase power relationships and then multiply them by a factor of 3. Those will also always work because these are where these quantities came from. So now let's talk about the constituent parts of our three-phase power. So we know, I'm going to summarize things up here, that S three-phase can be written as 3 multiplied by the magnitude of our phase voltage times the magnitude of our phase current with an angle of whatever impedance we have as our load. And similarly, we could say that S three-phase could alternatively be expressed as the square root of 3 times the magnitude of our line voltage times the magnitude of our line current with an angle theta z. Well, our average three-phase power is simply the real part of 3 Vp Ip angle theta z, which comes out to be 3 Vp Ip cosine theta z, which exactly matches what we derived earlier when we were looking at the instantaneous power. In terms of our line quantities, our average power is the real part of root 3 VL IL angle theta z, which comes out to be simply root 3 VL IL cosine theta z. For our reactive power, we're going to have the imaginary part of our complex power, which is going to be 3 Vp Ip sine theta z. And in terms of our line voltages and currents, we are going to have root 3 VL IL sine theta z, and our apparent power is simply the magnitude of 3 Vp Ip angle theta z, which is 3 Vp Ip. Over here, our apparent power is the magnitude of root 3 VL IL angle theta z, which comes out to be root 3 VL IL. And lastly, our power factor for our three-phase systems is simply the ratio of our three-phase power to our three-phase apparent power, which comes out to be just cosine theta z. And this is true for both in terms of phase quantities and line quantities. Okay. All right, so let's wrap things up here and talk about three-phase power factor correction. So three-phase power factor correction is interesting because we actually have two different options, okay? So on the left-hand side here, I'm going to put a balanced three-phase source. It does not remotely matter if this source is a Y-connected source or a delta-connected source. This is going to be my A terminal, my B terminal, and my C terminal. And then over here, I'm going to have my capital A, capital B, and capital C terminals for my balanced three-phase load. And once again, it does not remotely matter if this is a Y-connected load or a delta-connected load. Here I have my transmission lines connecting my source to my load. And if they have any impedance, that'll be okay too. But for now, for illustrative purposes, I'm going to leave them out. Okay. I'm going to make a copy of this so that I don't have to redraw it in a minute. All right. So let's talk about the first way that we could do this. Well, our first way that we can do power factor correction is to install a three-phase capacitor bank in a Y configuration. So here is our capacitor connected to our A phase. Here is our capacitor connected to our B phase. Here is our capacitor connected to our C phase. And then we tie all three of these capacitances together at some neutral point where all of these capacitors will have a value of what I'm going to call CY. Again, it literally doesn't matter if we have a delta connected source and load, we can still apply a Y connected capacitor bank to that system because our neutral connection for our capacitor bank does not have to be connected to our source or our load. Okay. The other option that we have is, I hope pretty obviously, a delta connected capacitor bank, which would look something like this. We would put some capacitance in between the A and B terminals, some capacitance between the B and C terminals, and then some capacitance between the C and A terminals, where all of these capacitors are given by C delta. Okay. Now, the math behind three-phase power factor correction is literally the exact same thing as the math behind single-phase power factor correction, except for one very specific caveat. Okay. So in single-phase power factor correction, we said that, let me write this down. Power factor correction. We had S cap, the complex power absorbed by our capacitor, was S new minus S old, where S new and S old were single phase quantities. And we found that C was equal to negative Q cap over omega times VRMS squared, where VRMS represents the voltage drop across the capacitor, okay? That's all O, and we could also write this as positive P old tangent theta old minus tangent theta new all over omega VRMS squared. The things that we have to pay particular attention to is to make sure that Q cap or P old are expressed on a per phase basis. So what I mean by that particularly is that we cannot use a single capacitor to do power factor correction across all three phases. We have to use one capacitor per phase to do power factor correction. So we need to make sure that we are determining Q cap per phase or P old per phase in order to use our equation. Another place that is potentially dangerous is our definition of VRMS, okay? These represent voltage drop across one phase of our capacitor bank. And the voltage, the numerical value of the voltage will be different if we connect our capacitor bank in Y as opposed to if we connect our capacitor bank in delta, okay? So let's work an example here really quickly that illustrates what I'm talking about. So a balanced three-phase source feeds a balanced three-phase load which absorbs a total of 24 megavolt amperes and operates at a power factor of 0.78. If the line voltages at the source are 34.5 kilovolts RMS at 60 hertz. Determine the value of C such that total load operates at a power factor of 0.94 leak. All right, so our total complex power absorbed by our load prior to power factor correction, which I'm calling S-old three-phase, is simply going to be 24 megavolt amperes with an angle of inverse cosine of 0.78, which comes out to be 24 angle 38.74 degrees megavolt amperes, or 18.72 plus J 15.019 megavolt amperes. P old single phase, which is the quantity that we need to plug into our equation, is simply the real part of S old three-phase divided by 3. Because for a balanced three-phase load, all three phases are going to contribute the exact same amount of average power. So this is going to look like 18.72 megawatts divided by 3. Let me find my calculator here. Should be able to do this in my head. Let's see, 6.24 megawatts. Still gonna need my calculator in just a moment. All right. Theta old is going to be the inverse cosine 0.78, which is our old power factor. We know that is going to be 38.74 degrees from a moment ago. Theta new is going to be negative the inverse cosine of 0.94. And the reason why we're using negative inverse cosine is because we are told that our power factor is leading. Anytime we have a leading power factor, we should have a negative angle. So this is going to come out to be negative 19.95 degrees. Okay. Omega is going to be equal to 2 pi times 60 hertz, or 120 pi radians per second. And then we have the quantity VRMS. And we're going to get two different numbers here. Okay. So let's consider first capacitor bank is Y connected, okay? I'm going to scroll up here to the previous page. So we aren't told whether or not our balanced three-phase source is a delta connected source or a Y connected source, and it literally does not matter. What we are told is that the line voltages have a particular magnitude, okay? So on our picture here, that would manifest itself as this, the magnitude of our line voltage, okay? The magnitude of our line voltage is very obviously not the voltage drop across our capacitor, because our capacitor is connected between this point and this point. So this voltage is VRMS, but we do have a transformation to go from effectively phase voltages to line voltages, right? So we know that our line voltage should be square root of 3 times larger than our phase voltage in magnitude. So from that, we're going to see that VRMS is simply VL over the square root of 3, or 34.5 kilovolts RMS over root 3. If instead our capacitor bank is delta connected, scroll back up here and look, we are given the magnitude of our line voltage, and it is literally identical to the VRMS that we're looking for. So VRMS is simply VL, or 34.5 kilovolts RMS. So from this, in a Y-connected bank, we would find that C is equal to P old, which we found to be 6.24 megawatts, times tangent of 38.74 degrees minus the tangent of negative 19.95 degrees, all over 120 pi radians per second multiplied by 34.5 kilovolts RMS over the square root of 3, this quantity squared, would give us 48.612 microfarads. For our delta connected capacitor bank, we would have C is equal to the same 6.24 megawatts, same tangent of 38.74 degrees minus the tangent of negative 19.95 degrees divided by 120 pi radians per second times 34.5 kilovolts RMS quantity squared. And this comes out to be 16.204 microfarads, which is exactly 3 times smaller. Actually, let me write this, Cy, C delta. So C delta is exactly 3 times smaller than Cy, which of course should make sense because we're dividing by the square root of 3 squared, which is the same as multiplying. We're dividing by 1 over the square root of 3 squared, which is the same as multiplying by the square root of 3 squared, or 3. Okay. So this brings up actually a pretty important question as well in a practical sense. Okay. If the capacitor C delta is always going to be 3 times smaller than Cy, why would you ever do 3-phase power factor correction using a Y-connected capacitor bank? And the answer is, it's all about the cost, okay? So the capacitor C delta is smaller by a factor of 3, but it has to handle a larger RMS voltage, right? 34.5 kilovolts RMS is significantly larger than 34.5 kilovolts RMS divided by the square root of 3. So how you install your 3-phase capacitor bank is always going to be driven by the cost, which is driven in some sense by the size of the capacitor, but it is also driven by the voltage rating of the capacitor. And so you would have to do a simple cost benefit analysis here to see whether or not it's cheaper to buy smaller capacitors with a larger voltage rating or larger capacitors with a smaller voltage rating to tell you which one to actually install in your system. All right, that is everything that I have for literally the entirety of the class. I will be around on Wednesday to answer any questions you guys may have about homeworks. I can prepare some example problems and all that kind of good stuff if you would like me to, but we're not going to be covering any more new material. The quarter ends on Friday, so I would appreciate if you were able to get your exams and homeworks and all that jazz to me at some point on Friday so that I can use the weekend to grade it and then get your grades uploaded before I head off for vacation. So you guys have any questions?
Yeah, Dr. Harmon, I got a quick question, but it's not about, the circuits. This is just about a general question.
Sure. What's up, Josh?
Do you know off the top of your head, what do we need, like a C or a D and technical writing to graduate?
You have to pass it.
So
a D works.
A D?
Yep. Just not an F.
Okay. All right. Thank you.
Yep. No problem.
All right.
Anything else? All righty. Well, thank you guys. And it's been a pleasure working with you all summer. And yeah, like I said, I'll be around on Wednesday if you need me for anything. If not, that's cool too. Let me know if you have any questions about your homeworks and all that kind of jazz, and I will see you later.